Welcome back. In this video, we are going to learn about maximum likelihood estimation. This method finds out the best values of parameters for which the model has the best fit. That is, your model is optimized. That means it finds those values of the parameters for the model you are dealing with for which the error is minimum. That means the difference between the predicted value and the true value is minimum. The finding procedure of this method is based on probability theory. That means it gives you some probability that determines the best fit for your model. Now, here we go with an example. We have some weights of packets in gram, and in the lower row, we have the packet count. That means frequency. That means 3 packets are there, which are weighing 1 gram. 5 packets are weighing 2 grams, like that. And if we plot this data over here, then you can clearly see that a cluster has formed here towards the middle of the scale, because you clearly see that the frequency is going high when it goes to the middle area, middle region. That means from 3 to 5 to 10 to 20 and to 30. And after crossing this middle region, it goes down again to 25, 20, 10, 2, and 1. That means in the middle portion, the number of packets is high that are weighing 5 grams. For this reason, we are having a cluster formation here in the middle region. Clear? Now, if we plot this data, what we will get? This is a scale for your weight. There's the x-axis. The y-axis is your density. Now, you can clearly see that from weight 1, it was here, and slowly it is going higher and higher and higher. And it has reached the maximum point here when the value of x, that is the value of weight, is somewhere here in the middle. It is not actually the proper measurement, what we have done here, but it is just an approximation, okay? So it has reached the highest point here. Then after crossing this middle point, it is going down again based on the data. So this is the middle point or middle region. And on the left hand side, it is going down from 20 to 3. And on the right hand side, it is going down from 25 towards 1, right? Now, if we have the left hand side, all these data points, and the right hand side, the data points as symmetric, then we say that this is a normal distribution. And this normal distribution is also known as Gaussian distribution. This normal distribution is based on 2 parameters. That means there are 2 parameters that decide the shape of this distribution or shape of this graph. The first parameter is mu, that is mean, and the second one is standard deviation, sigma. So these 2 parameters decide the shape of the graph. That means how it will look like. Now look at this figure. We have a mean of 4.854 and we have a standard deviation approximately 2.18, and the figure goes like this. We have a mean of same value, that is 4.854, and we have a different standard deviation now. There is a lesser standard deviation, that is 1.07, and for that the figure goes like this. It is much narrower than the previous one. Now in this figure we have the same sigma, that is 2.18, but we have a different mean, and the figure goes like this. Now the question is, which one of these above distributions will best describe the dataset? That means which pair of mean, mu, and sigma will give you a minimum error based on your dataset? Now, is this limited to 3 or something like that? No, you can have lots and lots of pairs of mu and sigma, and you have to find out which pair is doing good to minimize the error. And that is a tedious job based on a trial and error method like this. So you may argue that we can determine this mu and the sigma directly from the dataset. That means you add the values of data points and you divide that summation by the number of data points and you get the mu. Also, you can get the sigma by calculating the deviations between the data points and the mean. So what's the point of this trial and error business? Well, that's true in this case, but there are situations where a direct method of determining the parameter values is not available. In those cases, we have to fit in the values of the parameters to the system using some efficient method. Those predicted values must be as close as possible to the true values. That means the error between our predicted values and the true values is minimum. In this situation, maximum likelihood estimation will help you to find out that pair which is a good fit for your dataset. Clear? Say, for example, we take simple linear regression and we have the equation like this: y equal to w0 plus w1x. People sometimes used to write this as beta 0 and beta 1. And for example, you have this data set of 5 data points. So this is the values of x, these are the values of x, and these are the values of y. Now we have the values of x and y, and we know that there is a function f which is working between x and y, so that if we put in the values of x inside that function, the function will yield the value of y. That means whenever 3 is pushed inside the function f of x, the function gives you the output as 2.9. So the same case goes with the 6 and 3.1 also and the other data points. Now the question is, what is that function? What is the definition of that function? So that function's definition we have to figure out, right? Now it will be such a function so that the error is minimum. Now let us plot this data set over here, and we have the 5 data points. This side is x and this side is y. And this is a line that represents the definition of the function f. And for this, we have this equation that y hat is h of x, because it is not f of x, because we do not know the f of x. So this is an estimation. So that is h of x, and it is w0 and x0 plus w1 x1. So these are the two terms we add together and we get this y hat. Now this y hat is our estimated y, not the true y. Now what is x0? x0 is a bias, and we set the bias to 1, and this bias is associated with w0. So this x0 becomes a weighted bias. Now you have this x0 as 1, and you have x1 from the data set, that is 3, 6, 8, 2, 4. These are the x1s, right? Now to get this y hat, your estimated y, you must know w0 and w1. And the values of w0 and w1 will be such that this y hat will be as close as possible to y. That means the error between the y and the y hat will be minimum. So you have to choose such w0 and w1. So these are called learning parameters. Now, to find out the best line that gives you the minimum error, you have to go for two kinds of operations. First, you may have to rotate the line like this for adjustment, and for that, this w1 is working. And the other operation is shifting operation. You may have to shift the line up and down. For that, this w0 is working. Clear? So how much you have to shift and how much you have to rotate, that amount of rotation and shifting will decide the amount of error between y and y hat. So you have to find out the best w0 and best w1 that gives you a minimum error between y and y hat. So this y hat is your estimated y. So to get this y, you have the h of x, and it will go like this: w0 x0 plus w1 x1 plus the epsilon. This epsilon is the error term. So this part is your estimated y. That means your y hat. This is y hat. And you add this term, that is the error term, and you get the true y. So y minus y hat is your epsilon, that is your error. So we have to minimize this error to get the best fit. So the question is, for which values of y, w0 and w1, the line will best fit? Those values of what w0 and w1 for which the error is minimum. Now here is an assumption we have to go for, and that is very important. The distribution of the error, those epsilons, is assumed to be normally, independently, and identically distributed. That means i.i.ds. So you have like this: epsilon 1 for example 1 or data point 1, epsilon 2, like this you have epsilon n. So you have n data points or n examples, and you have n errors like this. Now this set of data, these epsilons, are normally distributed. That means you go towards the middle, it goes high, the frequency density goes high, and you go to the end and your frequency goes lower. So in such kind of distribution, we have to assume the epsilons are having. So we have our equation like this. This is the equation for the ith data point or the ith example. Your I ranges from 1 to n. And you have yi, that means the ith y, equal to ith w0, wi0, wi1 is ith w1, xi is ith x, and this epsilon is ith epsilon. And this part is your y hat, ith y hat. We follow the method of normal distribution because we have already assumed that the distribution of epsilons are normal, independent, and identical. Now the probability density of observing one data point, xi, generated from a Gaussian distribution. This is Gaussian or normal distribution. It will be like this: P of xi given mu and sigma will be 1 by root over 2 pi sigma square. Exponential part will be like this: minus xi minus mu whole square by 2 sigma square. Now this part is the deviation part, right? So to find out the best mu and sigma, we have to minimize this part. This is the error. This is the deviation, the squared deviation, right? Now if you put it in a conventional way, then you can go like this. You can write like this: root over 2 pi sigma square and e raised to minus xi minus mu whole square by 2 sigma square. That means this part is the power to e, right? The corresponding probability density function for one data point yi for linear regression will be like this, because we are interested in linear regression. So the corresponding data point probability density function for yi will be the simple: in place of xi, write yi, and in place of mu and sigma, we have w0, w1, and sigma square, right? Now this part is all right. This part is all right. Then exp, then this part you see, the power part. It was xi minus mu. That means you are taking deviation of those data points from mean and you are squaring those. Here you have to square the epsilon because epsilon is your deviation. Your target is to minimize the epsilon. That is why we have written epsilon I squared. Clear? And the meaning of this epsilon I is this: yi minus w0 minus w1 xi whole squared. Now this part is actually y hat, right? So yi minus y hat whole squared, and this division will be minimized. So we have found the probability density function, how it looks like in case of one data point for linear regression. Now we have to go for the whole data set. Now look at the probability function for all the data points of xi's in general. It is the product of the probability density functions for each data point. So this is the probability for one data point. Now you multiply all those probabilities up to n, from 1 to n, and you will get a probability density function for the whole data set. Similarly, for our linear regression, we will have the same thing like this. We had this part as the probability for a single yi, and you find out the product of these probabilities of yi's, and you will get the collective probability of your whole data set for your linear regression. Clear? So if you go for simplification, if you go for this multiplication, then you will get this part, this first term. There are two terms here. The first term is lower part is root over 2 pi sigma square, and the power is n, because n times you are multiplying this part, this first term. And the second term is e raised to this one, because this is a power to e. So the powers must be added. So if you add these things, then you will get exp of 1 by 2 sigma square, and this will be the constant, and this part is the summation part. Now this collective probability of the whole data set, we call it likelihood function. So this probability function is a likelihood function of the whole data set for linear regression. And this is also the likelihood function for a normal distribution like this. So we got this equation in the previous slide. And now we go for taking the log, because you know that first point is that we have to go for some derivation to find out the best fit. Now, if the expression is in product form, then it will be very difficult for you to find out the derivatives. So if the expression is in summation form, then it will be much easier to handle, right? And we can go for log, but before that, you check whether the expression here and the log expression is monotonically increasing function. So in this situation, we have that these functions in the log form as well as the general form is monotonically increasing, right? So we are safe to go with the log form. So we take on the left hand side. So this one is the left hand side, LHS. We take the natural log base e, and on the right hand side also we get for the log base e. Now whenever you take the log of your likelihood function, then you call it log likelihood function. Clear? Now we break up. First, there are two terms. The first term here and the second term here. Now apply the log rules. Log first term plus log second term. So log first term is this one. Log second term is this one. Clear? Next, you apply the log rule over this term. So this is in division form. So log of numerator minus log of denominator. Right? So this part is this one. And the second part is e raised to this. That means this is actually a power to e. So the power comes in front of log. So the power is here in front of log, right? So this is actually e. So log of e base e, and the power comes in front of the log, right? Okay, in the previous slide we got this. You change this to e, right? Log of e, log of 1 base e will give you 0. So this part will give you 0. So minus log of this portion base e will be here. So here also n by 2 is in the power, so it comes in front. So here you go. And log of 2 pi square, 2 pi sigma square base e. Now this part is over. This part is this part. So this is over. And on this part, only this portion remains. This portion remains because log of e base e will give you 1. Clear? Next. Now you split this part. Let me clean this up. Well, the first part is here. There is 2 pi, and the second part is sigma square. So you go like this, minus n by 2 log of 2 pi base e plus, in case of plus it will be minus because the minus is here. So minus n by 2 log of pi, sigma square. And this part will remain as it is. We open the first bracket, and due to this minus, the minus will be here. So we have reached the ultimate point. We have nothing to do any kind of algebraic application further. So finally, we get the equation like this. So this is the equation we have to use. So this is the equation we got in the previous slide. And now we have to go for the determining the values of W0, W1, and sigma square one by one. So first, we go for determining W0. So what will be the best point for W0? We can find the best point at for W0 where the derivative of this equation with respect to W0 becomes 0, right? Because that means it becomes flat. So that will be the best point for W0, right? So first we find out the derivative of this expression with respect to W0. So this is a partial derivative. So dou of L with respect to dou of W0 will give you this. See, based on W0 means this part is constant. So it gives you, it goes to 0. This part is also constant, goes to 0. And this part we have that minus 1 by 2 sigma square. So it is 1 by sigma square because this 2 is cancelled out due to this 2, because whenever you go for derivative, this power 2 will come in front, because we already know that d over dx of x raised to n will give you n x raised to n minus 1, right? So 2 comes in front, and that 2 and this 2 gets cancelled, and you remain with 1 minus sigma square. And you put this whole figure from here to here, over here. And then you go for derivation of this inner part. That means this portion. Right. So this portion, you have the yi as 0, w0 as 1, and w1 xi will give you 0. So the final derivative will be this. Now you set the derivative to 0. So you set this 1 by estimated sigma square, because you are going to estimate now. So we change the sigma to sigma hat, and this yi will be there because this is a true value, but w0 will be our estimate. So we write w0 hat. w1 will be our estimate, so it will be w1 hat, and this xi will be xi because this is coming from the data set, and we set whole this thing to 0. Now there are two terms in product form. The first term is this one, and the second term is this one, and these two are making this 0. So any one of them will be 0, right? So we are sure that 1 by sigma hat square, it cannot be equal to 0. So the second term is equal to 0. Clear? Now we apply the summation to each of these three terms. This is the first term, this is the second term, this is the third term. And we go for like this, that summation of yi minus n times w0 hat. Because when you go for this summation like this, that summation of I equal to 1 to n and w0 hat, you are actually adding w0 hat n times. That is why we have written n w0, right? And in case of the third term, you have w1 xi. Now, if you go like this, that summation of I equal to 1 to n, w1 hat xi. Now, if you have this, suppose this n is 3, then it will be looking like this, w1 hat x1 plus w1 hat x2 plus w1 hat x3, and you take w1 hat as a common factor, then you go like this, x1 plus x2 plus x3. That is the situation we have here. Now we move the w0 terms on one side and the other terms on the other side. So we have one w0 term here, that is n w0 hat. So we bring this term on the left hand side, and this term on the right hand side. So it goes like this. Now this n times w0 hat, if we move this n towards the right hand side, then it will be going like this. So 1 by n, the first term, minus w1 hat 1 by n, the second term. Clear? Finally, you have got this. w0 hat is y bar, because you are adding yi's up to n, and then you are dividing that sum by n. That means you are getting y mean, y bar, that is the mean of y. So this is equal to y bar. Here also the same thing, w1 hat will be here, but this term will be x bar. Now we will go for determining the expression for w1. For that, we have to find out the derivative of this L with respect to w1. And the derivative is like this. Here, this term is not having any w1 inside, so this will give you 0. This is constant. This is also constant. And this term we have to go for. Similar as before, this 2 is coming in front, and that 2 and this 2 will cancel out. So 1 by sigma square. And inside you go for this, write this summation, the whole term up to this part. You write the whole term. And now you get inside to find out the derivative of this expression. So for yi, it will give you 0. For w0, it will give you 0 this time, because you are going for derivation of with respect to w1. So this part will give you xi, right? So this xi, the derivative of w1 xi will be xi. So this xi is coming over here. Now you set this derivative to 0. So 1 by sigma square, and this term, the xi has been multiplied with each term inside. So xi yi, w0 hat xi, and w1 hat xi square equal to 0. Now out of these, the second term, that means this summation term, is set to 0, because the first term cannot be 0. So you push the summation inside as before. So summation of xi yi minus w0 hat summation of xi minus w1 hat summation of xi squared. Now this will remain as it is, and in place of w0 you put y bar minus w1 x bar, because remember, just a few moments back we derived that w0 hat is equal to y bar minus w1 hat x bar, and this term will be summation of xi, and this term will be remaining as it is. So we got this and we proceed. Now we go for this term will be remaining as it is, nothing we have to do here, but this will be splitted. Now y bar, summation of xi here, so this term comes out y bar summation of xi, and this w1 x bar will be associated with summation, so this part is coming out, right? So splitting this part will give you this as well as this, and the plus sign is due to minus dot minus, so these two minuses is giving you this plus, okay, and the last part remains same. Next, this part will be remaining as it is, and here we go, y bar is here, but the summation of xi's will give you n times x bar, because if you have the summation of xi's, now if you multiply n with the mean, then you will get the same summation, right? So in place of this summation of xi, we write n times x bar. This plus is this plus. This w1 hat will be this, and this x bar summation of this. This summation also will give you n times x bar, n times x bar. That means x bar dot n times x bar, that means n x bar squared. So that whole term will be w1 hat n x bar squared. And this we have nothing to do. So we got this. Now you rearrange the terms, the w1s on one side and the other terms on the other side. So w1 n x bar squared minus this one, you move this part to right hand side, right? Then it becomes w1 hat summation of xi squared minus w1 hat nx bar squared equal to this term, these two terms, this one and this one. Now we take w1 hat as a common factor, so inside this system goes, right hand side will remain same, and now we get this w1 hat equal to this part as the numerator and this part as the denominator. And we go like this, that if you go for xi summation of xi yi, and here you go for n x bar y bar, that means n times you are having this x bar and y bar. That means if you add x bar and y bar n times, then you will get the same result. So in place of n times x bar y bar, we are writing summation of x bar y bar. Here you go with the lower part. The first term remains same. And the second part, see, n times x bar squared. That means you can have the summation form like this. Summation of I equal to 1 to n x bar squared. So if you add the x bar squared n times, that means it will give you the same result as this one. So we got this. And for here, this numerator part, this part becomes this, and this part becomes this. Now we have to go for some deduction from where we have got this expression. So I will show you shortly, but before that, let us finish up this. Now we push 1 by n on the upper part as well as on the lower part, right? And this gives you sample covariance on the upper part, because you can see xi minus x bar, yi minus y bar, and the product term is divided by n, so it will give you sample covariance, and the square deviations from the mean, when you take the mean, then it will give you a sample variance. So finally, we got W0 hat is y bar minus W1 hat x bar, and W1 hat is giving you sxy by sx squared. Now, I promised before that I will explain you where from this numerator, this one is coming up over here, and the denominator is coming up over here. So let us start with the numerator part. So we will move back from here to here, because it will be very difficult to come down from this point to this point. So we will go from this expression to this expression, right? So xi minus x bar, that means this part, dot yi minus y bar, that means this part, we have to prove that this summation of xi yi minus summation of x bar y bar. So this is the part we have to prove, to be proved. Now here we go on the LHS, the left hand side, we just multiply this xi yi minus x bar yi like that. It is a simple thing. Next, this is a portion as it is, but here you pull the x bar out of this summation. So x bar comes out and inside goes the yi. Here also you pull out this y bar outside this summation, and here it is summation of x bar y bar, and it is actually n times x bar y bar. You already know that. So this part remains same, and this part is x bar, this is x bar, and this summation of yi will be n times y bar, right? Here also y bar is here, and this is n times x bar, and this is n times x bar y bar. So you got 3n times x bar y bar. This is number 1, this is number 2, this is number 3. So 2 of them with minus sign and 1 of them with plus sign. So you cancel any 2, 1 plus and any one of the minuses, and you remain with this part. So summation of xi yi, this term, minus 1 is remaining. So 1 minus xn x bar y bar is there. Now you can take the equivalent like this, that if this is the first part, it is as usual, and in the second part, second term, you have n times x bar y bar, so you can put it in the summation form like this. So you have got this, the right hand side here. So this is actually the right hand side. Next, we will go for the denominator part. Here also we will move back from this portion. From this portion, we will move back to this portion, the lower portion. Okay. So from here, we have to move to this part. So this is to be proved. So you take the whole square, that is xi square minus twice xi x bar plus x bar whole square, as you have done in previous in your school days, and you push this summation inside to these 3 terms, and look at the second term. The first term will be all right. The second term, you pull out this 2x bar out of the summation. So 2x bar is out of the summation, inside goes with the xi, and this remains as it is. Now the first term is not to be touched, nothing to do, but the second term, you see, it was 2x bar, so 2x bar is here, and xi is summation of xi's, that means n times x bar, and the third part remains same. So this is the first term, you don't have to do anything. You see the second term, 2n x bar whole square, 2n x bar whole square, and this third part is here. Now this x bar, n times x bar whole square means x bar whole square, you add n times, right? So this part is this, right? So you see that you have summation of x bar squared 2 times in front of this, that is minus, and here only one summation with xbar square. So if you go for arithmetic, then it will be like this. That is, this is the first term, and these two will give you arithmetically this. So this is the RHS we were looking for. Clear? So we have got this W0 and W1, and now we have to go for sigma square. This time we are going for finding out the derivative of L with respect to sigma square, and it will go like this. So the first term will give you 0. This is constant. But now the second term will work because sigma square is there. So you can find out the derivative easily. That is minus n by 2, minus n by 2, and log of sigma square base e will give you 1 by sigma square. So this is 1 by sigma square. So ultimately you will get minus n by 2 sigma square. And the last term will be like this, 1 by 2 sigma squared. If you go for derivative, I am not going into details. So I hope you know how to go for derivation. So this will give you 1 by 2 sigma squared whole squared, right? And this term will be there. And inside this term, you have no existence of sigma square in these three terms. So the whole term inside will give you 0. So you have nothing to do with this. Now you set the derivative to 0. So you set this whole term, that is from here to here, the whole term you set to 0. And a little bit adjustment you go for, that means you push this n by 2 sigma hat squared on one side and this whole term on the other side, and it will look like this. And if you go for finding out the value of sigma hat squared, this you will get. So 1 by n yi minus w0 hat minus w1 hat xi whole squared. That means you can clearly see that this is the variance we are looking for, because this is a true value, and this part is the estimated value, EV. So TV minus EV whole squared, whenever this whole squared, summation of whole squared is taken as mean by dividing by n, you will get the variance, right? So finally, I will list these terms, what we have got. So W0 hat will be like this, and W1 hat will be like this. Now for this figure, you can see that W0 hat is dependent upon W1. So before going for W0, you have to go for W1. So W1's determination will be the first job you have to do. The second job is the W0, and the third job will be the sigma squared, because sigma squared is dependent upon both W0 and W1. So this is the role of MLE, that means the maximum likelihood estimation, for finding out the best parameters for which the error is minimum in case of linear regression. So there are other statistical algorithms available for which you can apply this MLE method to find out the best parameters. That's all in this video.